The next few topics we're going to be learning about in class are all weather-related topics. We're going to be going over floods and hurricanes and tornadoes and winter storms and stuff like that. So today's lecture is going to be some background on the weather and the climate system. Now, when I took my first climatology class many years ago, my professor said there's a difference between weather and climate. Climate is what you expect, weather is what you get. Well, what did he mean by this? Climate is the average atmospheric conditions of a region over time. Weather are the atmospheric conditions, things like temperature, pressure, humidity, dew point, all that stuff, at a particular place and time. So this is what's like measured right now. This is the average. And when people are talking about the average climate, it's always important to know, well, what region are we talking about? Are we talking globally? Are we talking North America? Are we talking Southeast Texas? You know, what region are we talking about? And what time period are we talking about? Like, are we talking about average conditions over the past century, over the past million years, over the past 100 million years? Because those are going to be different. And so just make sure when you talk about the climate, you know what region, what area, and what time period we're talking about these average conditions being. And then just remember, weather is really the day-to-day and, in fact, hour-to-hour phenomenon measurements of the atmospheric conditions. So, what I have here, just to give you an idea about global climate over the past 550 million years. This is a geology class, so it's important to think about things in actual Earth history, right? Not just focusing on, well, the past 100 years. We want to know what the planet has behaved like for the long term. And so the past 550 million years is known as the Phanerozoic. This is the time period since we've had large, complex life and ecosystems. And on this chart, the average global temperature is shown in this line right here. And the higher that line is, that means the hotter it has been. The lower that line is, that means the colder it is. Now if we start out way back, 550 million years ago, just to show you where we are today, we're right there today. That's today's temperature. So 550 million years ago, it is significantly warmer than today. Then we have an ice house. This is a glacial time. Then it warms back up. We have another ice age down here, and warms back up. This time right here, that's the age of the dinosaurs. So you can see that throughout the age of the dinosaurs, again, it was significantly warmer than we are today. Now there's where the meteorite hit at the end of the age of dinosaurs. And remember I said meteorites can cause sudden global cooling. And that's what we see. It's sudden, but it also doesn't last that long. Warms up quite a bit, and for the time period since the demise of the dinosaurs, climate actually cooled significantly into this thing called LGM, is last glacial maximum. So that's the ice age. And then since the ice age, it has warmed up to about there. And so that's kind of our long-term temperature history of the climate system of Earth. And if you want to learn more about that, a great class to take is historical geology. We, in fact, talk quite a bit about why these different events and why we have such fluctuation in the long-term temperature record. So anyway, that's global temperature for 550 million years. We are still in an ice age. All right, now How do we know about those climates so long ago? Since people and thermometers have not been around for that long, how can I say in the age of the dinosaurs it was warmer than it is today? Well, that's because there are proxies for the climate. A proxy is something that stands in for something else. Like you can have a legal proxy who will stand in for you at like a hearing of some kind. So these are things that stand in for either temperature or precipitation records. So we can look at rock types or fossils or oxygen isotopes, and they will give us an idea of how warm it was, how cold it was, how rainy it was at different times in Earth's history. Now, obviously, climate has been changing, well, since Earth has been in existence. Now, as the whole point of that graph showing you the past 550 million years is that the climate has never been just static and unchanging. It's always warming a little, cooling a little, getting really warm, getting really cold. It's always in this change. So what causes those changes? What factors affect the climate system? Well, there's a bunch of them. For example, solar activity. Just how much energy is the sun giving off? Because when we talk about the weather and climate system, it's really the sun's activity that's driving a lot of that. The whole reason we have warm and cold fronts and hurricanes and stuff like that is because certain parts of Earth get more solar energy than others, and Earth tries to distribute that energy around. And well, then that depends on how much energy is the sun in fact giving us. Sometimes it gives us some more energy, sometimes it gives us some less, and that will affect the climate system. Also, the location of the tectonic plates affects things. Water and land absorb and reflect and give off energy in different ways. So if all of the plates are sitting at the equator where most of the sun's energy arrives, the planet's climate system is going to behave differently than if the continents are sitting at more polar regions, simply because, like I said, water and land deal with the incoming solar heat in different ways. Mountain ranges are important. Mountain ranges can be especially important when we look at precipitation patterns. Mountain ranges can block weather patterns, so they can cause deserts to develop in some places if mountains rise and prevent rain-bearing winds from getting to places again. And so mountain ranges can affect our climate system. Now here's an interesting one, the chemical weathering of silicate minerals. When silicate minerals chemically weather, now silicate minerals are the most abundant mineral in Earth's crust. When these things chemically weather, they actually pull carbon dioxide out of the atmosphere. So when you have major mountain building events, these mountains build up, that exposes a whole lot of silicate minerals to chemical weathering. You can actually draw down the carbon dioxide out of the atmosphere. And in fact, we see as the Himalayas rose and are still rising today, carbon dioxide levels significantly decreased. Back in the days of the dinosaurs, CO2 was around like 3,000 to 4,000 parts per million, and today it's like 400 parts per million. And so it's significantly less, and part of that is because of the drawdown due to the chemical weathering of silicate minerals. Also, the rate of seafloor spreading. So new ocean crust is generated at the mid-ocean ridges, and sometimes it's generated faster, which means seafloor spreading is happening faster. What this does then, this causes large-scale sea level changes. So small scale sea level changes, that's caused by how much ice, how many glaciers we have on Earth. Big sea level changes are caused by the rate of seafloor spreading. For example, at least 6 times in Earth's history, Texas has at least partially been covered by oceans. And those large-scale ones were caused by faster seafloor spreading. Well, how does this affect the climate? Again, it goes back to the water and land absorb and reflect light in different ways. If more land is covered with water, well, then the climate system is going to behave differently. Variations in Earth's orbit. These are called Milankovitch cycles. They're named for Milutin Milankovitch, who he was a POW in the First World War. And while he was a POW, he was a scientist. And so he worked on looking at how Earth's orbit varies and figured out that these variations can affect the climate system. And so we now call these Milankovitch cycles in his honor. And there's 3 parts to the Milankovitch cycles. The first is eccentricity. And this occurs on a 100,000-year cycle. Eccentricity is where Earth's orbit around the sun slowly goes from being circular to being more elliptical and then back to being circular. Being a cycle, it means it slowly goes circular, elliptical, slowly back and forth between those 2 endpoints. Well, if Earth travels farther from the sun, that's going to have a cooling effect on the climate system. Now, the second part of Milankovitch cycles is something called obliquity. And obliquity is how Earth is tilted on its axis. Today it's tilted about 23.5 degrees from perpendicular to what's called the ecliptic, how it orbits around the sun. But this changes a little bit. Sometimes Earth is tilted a little less towards the sun, sometimes a little bit more. Varies between something like 21 and 24.5, something like that. It's not much, but it is enough to affect how much sunlight reaches polar areas. If it's tilted a little more towards the sun, more light will reach the polar areas, which will have a warming effect on things. And then we have precession of the equinoxes. And it's quite interesting. Precession of the equinoxes, the ancient Greeks already knew that this existed. They didn't know it affected the climate system, but they knew it happened. And what precession is, you know, if you have one of those weird little toys you get in like cereal boxes and spin, like one of those tops, you know how the axis sort of wobbles? Well, Earth's axis wobbles as well. That's this precession of the equinoxes. So right now, the North Star is Polaris, but over time, the pole is going to rotate a bit and going to be pointing off towards Vega, and then it's going to wrap around and point towards Polaris again. So it's constantly kind of wobbling on its axis. And this is going to affect whether Earth's pole is pointed towards the sun in summertime or in wintertime. So again, this is one of these things that affects how much energy is reaching the polar areas, which is going to affect the climate system. So this is just a summary showing you your 3 changes: the eccentricity, the obliquity, and the precession. And they're all happening and affecting just how much solar energy reaches the planet. And being cycles, you know, you go slowly back and forth between end members. But they all happen at different rates. So here's eccentricity and obliquity and precession. And sometimes these cycles work together to make Earth's climate like colder. But sometimes some of the cycles fight each other. Like one of them will be trying to make the Earth warmer where the other is trying to make it colder, right? So you have different kinds of how they help or hinder each other. So what we're seeing right here, this is thousands of years. So here's today, there's 50,000, 100,000, and we'll go to like 150,000 years ago. This is putting them together, how much influence they have, whether they're working to warm the climate or cool the climate. And you can see here, they are kind of fighting each other a little bit, right? This is not going quite as cold or quite as warm as there. So they have quite a complex interaction to affect our climate system. But wait, there's more. There's more things that affect the climate system. Things like ocean currents. Ocean currents distribute heat around our planet. And there are some warm water currents, like the Gulf Stream, which is well known to bring heat northward here. But there's also cold water currents in some places. And so these act to help carry heat around the planet. And the reason why, for instance, if we look at London, look at the latitude of London. This is like up in Hudson Bay, Canada, where polar bears live. Well, you don't get polar bears in London other than at the zoo because you have this warm water current making northern Europe much warmer than it normally would be if you didn't have that warm water current. So these water currents, these ocean currents, can affect Earth's climate system. Now, we've already talked about volcanic activity affecting the climate system. You get enough ash and sulfur dioxide in the atmosphere that can serve to cool the climate. But we could also have an effusive eruption, an eruption that doesn't produce a whole lot of ash or things that go high in the atmosphere, but an eruption that does produce a lot of carbon dioxide. That could actually serve to warm the climate. So volcanic activity, depending on the size of the volcanic activity and the style of volcanic activity, can affect the climate system in different ways. Then there's something called albedo. Albedo is the reflectivity of a surface. So it's basically how much light gets reflected from something. So we have the sun shining here, right? And if you have fresh snow that's very light colored, it has 80 to 95% albedo. That means 80 to 95% of that incoming light gets reflected away. But if you have a dark surface, 5 to 10% gets reflected, the rest gets absorbed by that dark surface. And so depending on the albedo of Earth, more light will be absorbed or more light will be reflected, which will affect the climate. If you have more fresh snow and ice, like during a glacial time, you're going to have more light reflected, which means less energy, less heat absorbed. All right, ocean oscillations affect the climate. All right, an oscillation is something that goes back and forth between two end members. Okay, that's an oscillation. Probably the best known ocean oscillation is El Nino. And what do we talk about with El Nino? We're going to look in more detail at the end of lecture, but basically it's where a warm pocket of water and a cold pocket of water in the Pacific are, and every now and then they switch back and forth. Right? They oscillate back and forth. Well, depending where this warm and cold water is affects the climate. Now, El Nino might be the best known ocean oscillation, but there's the Pacific Decadal Oscillation, there's the North Atlantic Oscillation. There are these other oscillating warm and cold areas of water in the oceans which do affect the climate system, including both the temperature and also precipitation patterns. Who gets lots of rain and who ends up in a drought. Of course, Humans are part of the Earth system. We're part of the biosphere, and we can have an influence in the climate system. And but there's probably one of the most important things to recognize about the climate system, and that's all the things we don't know about or don't understand yet. In a system as complex as the climate system, it's foolish to be like, we know everything, we got it. And anyone who tells you that we know everything and we understand everything about it is lying to you, which is why I'm not going to say something so stupid. We don't yet understand everything about the climate system. Frankly, if we did, we'd get every weather forecast perfect, now wouldn't we? And we don't. So there are still many things, many subtle things that can occur in the atmosphere and in the oceans and throughout this great Earth system that can affect the climate that we still need to discover. So just remember, the climate system is complex, and there are many, many things that influence the global climate.